Welcome to The Explainer. Today, we're going to build a complete geometry toolkit. And believe it or not, it all starts with this one super simple idea you probably learned way back in 5th grade. We're going to see how that one idea unlocks the secrets of pretty much every shape imaginable.
All right, so let's just jump right in. I want you to forget about memorizing, dozens of complex formulas and theorems. What if I told you that all of it all just boils down to one single intuitive action? This isn't about rote learning. This is about understanding one core concept that ties everything together.
And here it is. This is the big secret, the whole key to everything. An angle, it's just a turn. That's literally it. Think about it. Every time you open a door, or turn a corner, or even just look up at the ceiling, you're creating an angle. The amount you turn is what determines the angle you make. So, okay, imagine this. You're standing facing forward. You spin all the way around until you're facing forward again. You just did a full turn, right? Well, in geometry, that's what we call a 360-degree turn. And that is exactly why there are 360 degrees in a circle. So if we follow that logic, what's a straight line? Well, it's just a half turn. You start facing one way, and you turn until you're facing the complete opposite direction. What's half of 360? It's 180 degrees. So here's the absolute key takeaway. The angles on any straight line will always, and I mean always, add up to 180.
You know, what's so cool about this is that all these fancy-sounding names, acute, right, obtuse, they're just descriptions of how much of a turn you've made. An acute angle, that's just a little turn. A right angle, like the corner of a book, that's a perfect quarter turn. An obtuse angle is a nice wide turn. And so on. It all comes back to that one simple action.
Okay, let's take this idea and build the first, and honestly, the most important tool in our kit. We're talking about the triangle. The triangle is like the fundamental building block of geometry. It's also why you see them everywhere in engineering, holding up bridges and buildings. And it all comes down to one magic number. And that magic number is 180. It seriously does not matter what the triangle looks like. It could be tall and skinny, short and fat, perfectly balanced. It makes no difference. If you add up the three angles inside, those three turns at its corners, they will always add up to exactly 180 degrees. There are absolutely no exceptions. And check this out. This property gives us a fantastic little shortcut. If you just extend one side of a triangle, see that angle it makes on the outside? That's called the exterior angle. And here's the cool part. That exterior angle is always equal to the sum of the two interior angles that are furthest away from it. It is such a handy tool for solving problems in a snap. So let's pause for a second. If we've really nailed down the triangle and its magic number of 180, does that mean we've kind of secretly mastered every other flat shape too? Well, the answer is, yeah, pretty much. Let me show you how.
Okay, so let's take a look at a more complex shape, something like this seven-sided figure, which is called a heptagon. Trying to just guess the sum of its internal angles, that seems impossible, right? But here's the thing, we don't have to guess. We just need to go back to that 5th grade idea. We break it down into the one shape we already know everything about.
And the method for doing this is so simple. Watch. First, you just pick any single corner, anyone you want. Second, from that one corner, you draw a straight line to every other corner you can get to. And third, just count up the triangles you just made. So, when we do that with our seven-sided shape, what do we get? Exactly 5 triangles. Now, think about some other shapes for a sec. A square has 4 sides, and that gives you 2 triangles. A pentagon with 5 sides gives you 3. Are you seeing the pattern here? It's always the number of sides minus 2. And this is where the magic happens. We've got 5 triangles, right? And we know for a fact that every single one of those triangles has angles that add up to 180 degrees. So the total for the whole heptagon is just 5 times 180, which gives us a grand total of 900 degrees. Simple as that. And boom, that right there gives us the master key for any polygon. For any shape with n sides, the sum of its inside angles will always be the number of sides minus 2 times 180. This isn't just a party trick. This is the rule that designers and even 3D animators use to build entire complex worlds out of simple shapes. All right, and here's a quick bonus tool for your toolkit. This one's pretty wild. While the inside angles change depending on the shape, the sum of the exterior angles, the turns you'd make at each corner if you were walking around the outside of it, that sum is always 360 degrees.
For a square, a pentagon, a dodecagon, it literally does not matter. It's always 360, always.
Okay, let's add the next major tool to our kit. And this one is like a powerful cheat code for solving all kinds of geometry puzzles, especially ones that have parallel lines, which, are just lines that point in the exact same direction and will never, ever cross.
So when you have a third line, we call it a transversal, that cuts across two parallel lines. It creates this beautiful, predictable pattern of angles. You just have to know 3 rules. First up, we have corresponding angles. See how they're in the same spot at each intersection? Well, they're always equal. Next, look for a Z-shape. That'll help you find the alternate interior angles. And guess what? They're also always equal. And finally, if you can spot a C-shape, you found co-interior angles. These guys are a little different. They always add up to 180 degrees. Seriously, learn these 3 rules, and they become your geometry cheat code.
All right, let's take a breath and recap. We have now built a complete toolkit, all based on that one simple idea of a turn. We've got our rules for lines, for triangles, for any polygon, and now for parallel lines. So it's time to put on our detective hats and actually use this stuff to solve a problem.
Okay, here's the case file. We need to find the size of each interior angle in what's called a regular pentagon. Now, we know a pentagon has 5 sides, but that word regular, that's a super important clue. It means all the sides are equal and all the angles are equal. So, with what we know, how would you even start? Well, the first thing we do is grab our master key for polygons, right? A pentagon has 5 sides, so we just plug that into our formula. The number of sides, 5, minus 2, times 180. So that's 3 times 180, which gives us a grand total of 540 degrees for all the interior angles combined.
And now, for the easy part, the final step. Because we know the shape is regular, it means all 5 of those angles have to be exactly the same. So we just take our total of 540 degrees and divide it by the 5 equal angles. And what does that give us? Our answer. Each interior angle in a regular pentagon is exactly 108 degrees. Case closed.
Now, as you get better at being a geometry detective, you do have to watch out for a few common traps. It's super easy to forget that a 4-sided shape is 360 degrees, not 180. Or to get your parallel line rules mixed up. Oh, and a big one. Never, ever assume a shape is regular unless the problem specifically tells you it is. And finally, just do a quick mental check at the end. Does an angle of 108 degrees look about right for a pentagon corner? Yeah, it does. That little check can save you from some really simple mistakes.
So what's the big idea here? What's the main takeaway? It's that geometry isn't just some dry, abstract subject stuck in a textbook. It's literally the blueprint for the world all around us, and it's all built from that one simple idea of a turn. You'll see it in the honeycomb of a beehive, in the architecture of a massive skyscraper. These rules are absolutely everywhere. So the real question is, now that you have the toolkit, where are you going to see it now?
For thousands of years, there's been this simple riddle that's fascinated some of the greatest minds out there. How do you build something absolutely perfect, using just something to draw a circle and something to draw a straight line? Well, today, we're going to solve it. I want you to imagine for a second that you're an ancient Greek architect. You've got to build a perfect square, or find the dead center of a circle, or split an angle exactly in 2. You don't have rulers with little markings, no digital protractors. So how in the world do you get something that's not just close enough, but absolutely 100% perfect? How do you create certainty itself? Well, you've really got 2 choices. On one hand, you could try measuring, but let's be honest, that's always going to be an approximation, right? A pretty good guess. Or you could try constructing. Now, this is a whole different ballgame. It's not about guessing. It's about using pure logic to build perfection, where every single step you take is guaranteed to be correct. And the only tools you're allowed? A compass and a straight edge. That's it. Now, to play this game, you only need to understand 3 really simple ideas. But from these 3 little building blocks, believe me, we can construct an entire universe of perfect shapes. So first up, we have the point. Think of it as a pure idea of a location. It tells you where something is, but it has no size at all. It's an infinitely small dot. From points, we get the line. And again, it's not just the line we draw with a pencil. It's the idea of a perfectly straight path that just goes on forever and ever in both directions. And our third and final concept is the circle. This is what a compass is all about, right? It draws every single point that is the exact same distance from a center point, creating this perfect shape that's defined by one simple, unchanging rule. Okay, so here's a quick cheat sheet for how these things play together. These are the fundamental truths we can always rely on. A straight line is always 180 degrees, a full turn all the way around is 360, and when two lines cross, the angles opposite each other are always identical. We're going to need these later, so keep them in your back pocket. These basic rules are really the foundation for the genius of Euclidean geometry. The idea is so simple but so powerful. Let's just agree on a few things that are super obvious, and then, using only logic, we can prove everything else. No guessing allowed. All right, now that we've got the rules, we can actually start building. These constructions, they're not just drawings. They are logical arguments made visible. So let's see our first power move in action. Okay, so here's the challenge. I give you a line segment. No rulers, remember. How can you find its exact midpoint and, just for fun, draw a line that's perfectly 90 degrees to it? It seems impossible without measuring, but it's not. Here's how you do it. First, set your compass to any width that's clearly more than halfway across. From one endpoint, you swing an arc. Then, and this is the most important part, without changing the compass width, you swing another arc from the other endpoint. See where those two arcs cross? You've just created two new points. Connect them with your straight edge, and boom, you're done. That's a perfect perpendicular bisector. Okay, that's the how. It's kind of neat, right? But the real beauty, the real power, the part that should really make you go, whoa, comes from asking the next question. Why on earth does that actually work every single time? Well, the secret is hidden in the triangles we've accidentally created. Because we never changed the compass width, we know that all four of these diagonal lines are the exact same length. This forces the two big triangles on either side to be perfect mirror images of each other. And if the triangles are identical, then all their angles have to be identical too. That guarantees, absolutely guarantees, the line is cut perfectly in half at an exact 90-degree angle. It's not magic, it's a logical certainty. So that construction we just did, it actually reveals a deeper, much more powerful concept. We're about to unlock the master key to solving these kinds of puzzles. And it's this idea of a locus. Now, locus sounds all fancy and complicated, but the idea is wonderfully simple. It's just a path of points that all share some kind of property. The best way to think about it is like a dog on a leash tied to a pole. The rule is, stay within the leash's length. The path, or the locus, that the dog can trace is a perfect circle. The rule defines the shape. And this is where the light bulb should really go on. The set of all points that are equally distant from two fixed points is the perpendicular bisector we just built. The set of all points that are equally distant from two intersecting lines is an angle bisector. All of a sudden, you realize that every construction is really just finding where two of these paths, these loci, cross each other. And this right here is the big secret. When you get one of those really tough geometry problems, like in a math competition, it's almost always a locus question in disguise. The problem is secretly asking, given these rules, what is the path this point must follow? If you can learn to think in terms of loci, you can solve problems that seem completely impossible. So at this point, you might be thinking, this is pretty cool, but what's the big takeaway here? Why does this ancient game actually matter? And that is an excellent question. It matters because we've just assembled a complete logical toolkit. We have the rules, we have the construction tools, and now we have the master strategy of thinking in Loki. Let's see what this powerful combination lets us build. It really boils down to this formula for success. Constructions are your tools, thinking in loci is your strategy, and those basic properties of triangles and angles, those are the rules of the game. You put them all together and you have an incredibly powerful system for finding the truth. And that brings us right back to our very first question. This is how we build certainty. We started by asking how to find the middle of a line, but the exact same logical foundation is used to prove some of the most complex and beautiful ideas in all of mathematics. Every step is built on the last one, creating a perfect, unbreakable chain of pure logic. So ultimately, this whole thing is about a shift in mindset. It's about moving away from guessing or just measuring, and instead, adopting the geometer's mindset, which says, every single step I take must be logically guaranteed. No assumptions, no approximations, just proof. And that leaves us with one final thought to chew on. we've seen how a few simple, obvious rules can be used to build a whole world of perfect, undeniable geometric truth. And it just makes you wonder, if pure logic can build all of this, what else can it build?